Hello, Calculus kids. This video is going to go over some information from section 1.4. It's dealing with continuity and removable discontinuity and understanding on what intervals a function is continuous and where it is possibly not continuous. And to start off, I want to show you here the criteria for continuity. So in order for something to be continuous over some interval at C, at a particular point, okay, at a particular C value, the following three conditions have to be true, okay? You have to actually have a value for f of c. So f of c has to be defined, okay? F of c has to exist. It has to be defined. It cannot be undefined. That's the first thing that has to be true. The second thing that has to be true is the limit as x approaches c of the function f of x has to exist. Okay, that's the second criteria. The third criteria for the function to be continuous at c is the limit as x approaches c of f of x has to equal f of c. So what it's saying is the limit has to actually equal the value at c. Okay, the limit at c has to equal the value at c in order for it to be continuous. And this will make sense. So I'm going to show you here on some graphs and what I mean by that. So here are some graphs that are discontinuous, which you can totally tell they're not continuous, right? There's a big problem. So we're going to look at each one and talk about each one. So here, we're always looking at C. We want to know if it's continuous at C. Well, there's a hole there at C. There's no value at C, okay? So C is not defined. The function is not defined at C. So that cannot be continuous at C. Here, you'll notice C is defined. C is defined at C. It's defined right here, but the limit does not exist. Can you see that? If we had our little man walking down this one and up this one, we would not come to the same place. So the limit does not exist there. Here, the limit exists, okay? There's a value for C. Here there's a value for C right there. The limit exists, but the value for C is at 1 and the limit is at 3, and those two are not equal to each other, so it's not continuous at C. And here at C, we have an asymptote, so there is no limit at C. So just like this one, there's no limit. The limit is undefined, the limit does not exist, so you cannot be continuous at C. If the limit doesn't exist at C, then it is not continuous at C. The limit has to exist, there has to be a value at C, and that limit has to equal that value at C. Okay? If those three things are not true, then you do not have continuity at that point. We're going to talk about removable discontinuities a little bit and asymptotes, which we did discuss a little bit earlier. So we're going to use all of our checks here and figure out if we have a problem. Obviously, we might have a problem at 0, right? We could have a discontinuity at 0, and you guys know that we have an asymptote here at 0. All right, you guys know that from previous courses. So it's discontinuous at 0, okay? All right, now what if you're before 0? What if you are the interval before 0, okay, from negative infinity to 0, okay? Is it continuous on that interval? And yes, it is. It is continuous on that interval. Is it continuous if you go from 0 to infinity? That's all fine. Really, any number is going to work in there except for 0, okay? So it is continuous on these two intervals here, okay? And this is a non-removable, discontinuity. It's not a removable discontinuity, okay? It's an asymptote happening here at 0. Now with number 2 here, we're looking at maybe some problems in the denominator here. So what I'm going to do is I'm going to factor this, x plus 4 on the top, we're going to factor the bottom and get x minus 6 and x plus 4. Okay, now this is what we talked about the other day. If these cancel out, okay, now before we have two potential problems, right? X equals 6 is a potential problem and x equals negative 4. Those are two potential problems. What's happening at x equals 6? That's the asymptote, okay? That's a non-removable discontinuity, okay? So this is non-removable discontinuity. Now at x equals negative 4, that's a removable discontinuity. That's where the hole is going to be, okay? Now if we are between negative infinity and negative 4, we're okay. And if we're between negative 4 and 6, we're okay. And if we're between 6 and infinity, we have continuity. But the discontinuity is happening at those 2 points. Okay? I'm going to do 2 more with you. This one, you know this. This is the sine. This is your sine curve, okay? This is continuous, always continuous. There's not a problem anywhere, or a removable discontinuity or a non-removable discontinuity. So it is continuous for all numbers between negative infinity and infinity. So for all real numbers, okay? This one here, I want you to look at this one here. We have a potential problem here, okay? Our potential problem is going to be at 0. This is a line, it's continuous, right? This is a parabola, it's continuous. The place we're going to have a problem is when x is 0. So what happens when x is 0? If x is 0, up top we are going to have x plus 1. When x is 0, we are going to have 0 plus 1, which equals 1, okay? When x is 0, if I use this one, so now we're gonna look at, so when x is 0, so basically, let me just rewrite this. H of 0 has to equal 1, okay? So we actually have a point at x of 0. Now the limit, in order for this to be continuous at 0, the limit coming from both directions, it has to have a limit, and that limit has to be 1. So let's look at the limit as x approaches 0, okay, from the right, okay? So we're coming from the positive and going to the right. So I'm going to be anything greater than 0, so I'm going to use this one. So we already know the limit coming from the right of h of x is going to be 1, because I'm going to plug 1 in here. Now what if I do the limit as x approaches 0 from the left? Okay? From the left, that's less than 0. So we would use this function. So if I plug a 1 in and I square it, if I plug a 0 in and I square it, I'm going to still get 1, right? So this equals 1. And we have, those are the same, right? So the limit is 1, okay? The limit is 1 and the actual value is 1. So there is no discontinuity, okay? It is continuous on all real numbers. Okay, now what I would like you to do is I would like you to try this one. Okay, let's see how you did, okay? The possible discontinuity is at 2. Okay, that's where you're going to have a possible problem. These are just parabolas, so they're continuous. If you don't have a restriction on them, they're continuous. So we plugged in f of 2. We have to see if there's actually a value at 2. So when we plug in f of 2, we would use this equation, because this is the equation where x can equal 2. So we end up getting 6, okay? Now, if we try to find the limit from the left, okay, if we're coming from the left, we're coming from the left side of 2, we would use this, because when x is less than 2, we would be coming from the left side of 2. If we find the limit, we basically plug in 2, we get 2. If we're coming from the right side, okay, we would be coming using this function right here, and we would be coming from the right, and we would plug in 2 to this function. We already know that that's 6. So basically, if you're coming from the left, you're going to end up at 2. If you're coming from the right, you're going to end up at 6. It's not the same spot. So the limit does not exist, okay? And the limit the limit does not exist, then we cannot have continuity at that point. Okay, so there is a discontinuity at 2. And that's it for this one.